Yes,
I will
please.
start.
Get going. Sorry if.
No, I just, you cut out for me for a second. Okay, great. Thanks very much, Craig, for the invite, and thanks everyone for coming. I see lots of familiar faces on the participants list, so hopefully will not disappoint overly in discussing this. So I noticed that, the overall theme of this set of talks are sea level rise. And so I wanted to think of the thing that both informed sea level rise, but actually was kind of the most exciting scientific discovery in our group along those lines. And so I settled on this, talking about this project, which was actually an undergraduate thesis project by student Galen Hall, who was a physics undergrad. And this is the title of the paper we've submitted, but I'll actually put it in a broader context with some of the other student work in my group and, IPCC sea level considerations as well. So when we think of the broader IPCC perspective, we have hockey sticks, we have observed versus simulated, including and excluding natural forces for surface temperatures. And we know that in some deeper sense, the surface temperature is really linked intimately to the energy budget of the Earth, and in particular, the upper ocean energy budget, which is where most of the excess anthropogenic energy ends up. And so this surface temperatures don't drift that far from the sea surface temperatures. And that link up is something that's worth thinking about as a fundamental aspect of how the Earth system works. And then we also have a hockey stick for sea level. So our hockey stick for sea level tells us that, we have an unprecedented sea level rise since 1900 over the last few thousand years. And that's, an observable, but there's an additional link up that was really highlighted. And I know Matt Palmer's already spoken in this series, so I don't fear stealing his thunder, but the key link up between those aspects as far as the AR6 presentation comes down to the global energy inventory sitting side by side with the global sea level budget. And so Matt made this figure. This is a great figure. It has the same color scheme on both sides. So you really are invited to conflate the idea of the sea level budget, the thermal expansion of the oceans, together with the uptake of energy by those same layers within the oceans. And so part of the thinking behind this was a series of papers that talked about using emulators to do both the energy budget and the sea level budget. Matt's 2018 paper being a really excellent example along those lines. And so that's sort of the launch point for what Galen worked on that I want to talk to you about, because we didn't really fully, well, there's some mysteries that I hope we've resolved a few of. There's still some remaining mysteries to go, even with that part resolved.
Baylor, can I interrupt you for a moment?
Sure.
There's a couple of people in the chat talking about, and for myself as well, there's a sort of couple of black boxes covering one, or blue boxes.
Oh, let me close some of the things that are up here that maybe will make things a little clearer. Oops.
Thank you.
More, if I hide the video panel and hide the meeting controls, is that better?
Yes, yeah, you seem to be getting it. There's now unfortunately a box in this. Oh yeah, it's all gone now.
Okay. So let me jump back then and make sure that everybody got the gist here. So on the left here, we have the global energy inventory, and on the right, we have the global sea level budget. And so the sea level budget is either from expansion of the oceans or from the addition of mass for the global sea level. And so, the ocean layers here, the upper kind of mid-depth and abyssal are these three upper layers. And then on the left, the same layers of the ocean, but in terms of their contribution to the excess energy budget are laid out. And these are using similar modern observational data in both cases. And so the idea was to invite you to think maybe there's some kind of similar processes going on between these two. That was the idea in the IPCC presentation of these side by side. But there's also a tool, a key tool that was used for the AR6, a 2-layer model emulator that goes back to work by Jonathan Gregory and Isaac Held and Mike Winton and others that I want to use as the launching point for what we're going to talk about today. And not surprisingly for anybody who's seen me give talks before, this is going to loop around and come back to the mixed layer in some sense. And we got very interested in whether the upper layer of that 2-layer model has anything to do with the mixed layer. And it turns out that's actually a rather complex story. So this is just showing the annual cycle of the mixed layer from a now relatively old observational data set, but it gives you a sense of both the magnitude and the variability. We could do much better now because we have quite a few years of Argo data examining the mixed layer, but I haven't made an updated movie of that yet. But the point here is it's tens of meters in the summertime hemisphere and hundreds of meters in the wintertime hemisphere. And there is a lot of structure to the mixed layer, which has to do with different processes like deep convection, mesoscale eddies, interactions between fronts and surface forcing, all those kind of things contribute. Okay. So what's the mixed layer if we think of it from the perspective of an energy budget? This is a nice slide that came that I found online a few years back, which just kind of puts a lot of the things together. We're thinking about the mixed layer as being a reservoir for energy in this larger energy budget, which has incoming solar, long wave recycling between the ocean and atmosphere, greenhouse gases, outgoing long wave, and potentially entrainment at the base of the mixed layer, or some kind of connection between the mixed layer and the deep ocean. And you can put that together into a simple budget of this sort. And so you have like a top of atmosphere energy imbalance with a bottom of the mixed layer, some heat capacity, giving you a rate of change of temperature of the mixed layer of this coupled atmosphere mixed layer. The mixed layer tends to have about 30 times as, well, between 3 and 30 times as much heat capacity as the whole of the atmosphere. So effectively, the temperature you're talking about here is the mixed layer temperature. It's in this little simple model. And not to forget to mention our Nobel Prize, if we think of a system, a heated kind of test tube with some water in it, there is the Hasselman and Noel model from the mid-70s that essentially says that same thing. It says that the temperature change of an upper ocean layer should have something to do with the random atmospheric forcing. They don't have the entrainment aspect here, but that's because they're thinking of the mixed layer as having a fixed depth rather than a time variable depth. And the reason they do that is basically to make this a linear equation that they can solve. Then they have stochastic atmospheric forcing and some restoring timescale back to a climatological temperature. And if you solve this simple stochastic differential equation, here's some example solutions down here from their paper, you can get something about the temperature variance per unit frequency, so the power spectrum of temperature variance in this mixed layer versus the frequency of forcing. And you get these kind of profiles which go from having no restoring to having a pure red profile to kind of a reddened profile from some time scale to lower frequencies. You roll off to white, but you're kind of red over those from the synoptic variability up to whatever that time scale of the roll off is. And the important point here is, one, this is a nice way of thinking about how you can think about the role of the ocean in the climate system as just a kind of flywheel on the random atmosphere going above. But depending on what this restoring time scale is, which depends on lots of parameters down here, but also the mixed layer depth and the heat capacities, or effectively how much is the inertia of the system you're trying to warm up or cool off with this atmospheric forcing, you can get a very wide variation in terms of what the ocean temperatures do in response to random atmospheric forcing. I didn't put the slide in this talk, but it's quite straightforward to solve this same system for a something like a 1% per year CO2 increase, or a step function of CO2 increase, and to take that forcing and to solve this same system. And again, this time scale of response is something that's key to what the response looks like. And so then when we try and think about this in the slightly more realistic global ocean setting, you start to think about these simplified models. So the one from Anand Nanadesikan is a nice one to think about, which now brings us into thinking about a Southern Ocean overturning, a Northern Ocean overturning circulation, upwelling, separation of a few water masses, maybe the water mass at the surface and the water mass at depth. And importantly, there's geographic variability. So there's quite a different process going on in the tropics than going on in the Southern Ocean and going on in the Northern Ocean. We know that that has to do with eddies and Ekman transport in the Southern Ocean, and has to do with all of the intricacies of deep convection in the Northern Oceans. But this is one thing to have in mind, but this doesn't obviously tell you what the time scales of variability in the Hasselman sense would be, or even whether you have a Hasselman model kind of sitting on top of this, just governing a mixed layer, or how it fits together in a kind of simplified model sense. Even simpler than this Nanadesikan model of 2 layers with regional variability, there's the 2-layer homogeneous energy balance model, which derives originally from this paper by Jonathan Gregory, but as I said, got used by quite a few papers. And so what the target here is we'd like to synthesize some of these simple models of the global ocean that have some regional specificity, plus some dynamical semblance to the Hasselman model, or maybe the 2-layer energy balance model, and put them together in some kind of synthesis that allows us to better understand why the ocean takes up the amount of energy it takes up in different classes of models, and also the thermosteric sea level rise implications that go along with that. So here's Galen. And so the question we set out was, does the mixed layer affect climate change? And we expected to find basically that Hasselman was mostly right, and that is definitely not what we found. And we also expected, it took great insight on Galen's part to recognize that the right thing to do after Hasselman was to jump onto this 2-layer EBM and use it in a specialized way, which builds off of the work of Geoffroy and others in about a decade ago. Okay. So here's the 2-layer energy balance model, written with the standard symbols up here on the right-hand side. So there are heat capacities for a surface layer, or maybe the active layer. It's the one that changes quickly in response to temperature, to surface forcing. And then there's a deep layer, and there's a forcing variable F. There's a restoring timescale, just like in the Hasselman model. So if you neglected everything except for the first 3 terms in this upper equation, you're effectively the same as the Hasselman model. And then there is an exchange between the surface layer and the deep layer with some parameter gamma that's giving you the sort of exchange coefficient between the two. And then importantly, there's this epsilon, which is the efficacy, which is a concept introduced in a nice paper by Mike Winton in 2010. And the efficacy parameter is key because it basically says when you have an anomaly of the surface ocean to the deep ocean, does this system resolve that anomaly by sending it down to the deep ocean, which is what would happen if epsilon was equal to 1, or does it resolve it by some exchange with the atmosphere through long wave radiation or air sea fluxes or cloud changes? All those things are parameterized by this single parameter epsilon. And we'll come to see that that has an important part to play in the story we're going to tell. So how do you figure out these parameters? Well, an important aspect is almost none of them are measurable in the real world. The surface temperature is certainly measurable. The deep temperature is measurable, but the heat capacity that goes along with the definition of what that surface temperature is not so obvious. Which water mass is the water mass that makes up the surface temperature change? Which water masses are the ones that make up the deep temperature? You don't even know what the volume is that heat capacity is supposed to apply to a priori. Similarly, this exchange coefficient buries a bunch of different processes, both the northern overturning, the southern overturning, eddy-induced vertical transport, all of those things are all captured within gamma. And then lambda, this restoring timescale, is also a parameter that's subject to interpretation, as is the f, because as you change the other parameters to even contemplate what the relevant f is, you have to figure out all of these pieces together. So there is a process which Geoffroy and company figured out to doing this, to estimating these parameters, that has something to do with examining the time series of an evolving system like this over a few hundred years of simulation time. On the left, we're showing in the gray spaghetti plot a mess of CMIP6 models, all the CMIP6 models that were available at the time that we collected this work together. I think this is a quadrupling of CO2 experiment that's shown, but we also use the 1% per year simulation. And then in the dark black line is the multi-model ensemble mean. And the point here is that at the beginning, you get a very rapid increase, which has most to do with this active surface layer, the active layer. I use the term active layer to make you think about permafrost. It's the part that's changing quickly under variable forcing, versus this slower response, which involves the equilibration of the exchange between the deep ocean and the surface ocean. And so if you take this analysis, if you take this aspect here, where you're looking at the early time versus the late time, and you project that on the right-hand side panel between the top of atmosphere watts per meter imbalance on the vertical axis, and then the surface temperature change on the horizontal axis, you see the open circles are during this short T sub f period, right at the beginning of the run. And then the solid dots are later in the run. And quite obviously, there's a different slope between those two, which means that you can differentiate between the fast response of the surface layer and the response that involves the later layer by optimizing those two slopes, which depend on these parameters in the model. So that's the way that we essentially tune a two-layer model to match one of the CMIP6 models. That's the same thing that everybody does to do this process. That's essentially the same mechanism that Palmer used, that Geoffroy used, that gets used over and over again. So each CMIP6 model from every modeling center around the world has its own set of parameters. And then the question is what do those mean? We can't observe any of them, or hardly any of them, in a meaningful way, except for through a tuning procedure. So you might say, well, okay, the surface ocean layer, this active layer, convert that to units of mixed layer depth or something like that. Like, how deep is that layer? And it turns out that it's between about 30 meters and 75 meters, which is not dissimilar to the mixed layer in terms of its volume, but it is geographically uniform, whereas the mixed layer has important geographical variability that's not part, and seasonal variability that's not part of this surface layer definition. So Jonathan Gregory pointed this out in one of his early papers on this topic, that you really shouldn't think of this active layer as being interchangeable with the mixed layer, or you should at least be cautious before you do so. And what I'm going to show you is that they are quite distinct notions in most of the world. But in order to do that, we not only had to look at the mixed layer, but we had to break it down into three regions: a Southern Ocean region, a Northern Ocean region. So you can see these white stripes are indicating the region. And we just did zonal mean for these, which is fine for the Southern Ocean. The Northern Ocean is mostly just ocean in the North Atlantic. So it's essentially the same as the North Atlantic mixed layer depth. And then a tropical ocean, which is basically a band including the equator around the center of the Earth in latitude space. So we have three regional mixed layer depth that we're going to think about averaging. We're going to fit these parameters, and we're going to see whether there's the relationship between those two. And here's one really important aspect, which is you might say, oh, well, as the climate is changing, the mixed layer depth is probably changing too. And it is. And in fact, it is for all of these different models. Interestingly, if you sort them by, the shallowest Northern Ocean mixed layer to the deepest Northern Ocean mixed layer, that rank order of the models does not change very much over the course of these climate change simulations. So if there is a correlation between mixed layer depth in these regions and these model parameters, which are chosen to be constant in time, it would not be changing necessarily throughout the run. And so after validating that, we decided that actually the key metric that we care most about is not the mixed layer depth that evolves in time over the course of a simulation, but the mixed layer depth at the initial time, the 1850 mixed layer depth. So we can sort all of these models into what their mixed layer depths are at 1850, and we can ask whether those mixed layer depths have any relationship to these key parameters in the two-layer model. Once we have the two-layer model, past work, like these references above and the one by Matt Palmer that I mentioned, shows that we can actually predict quite accurately both the equilibrium climate sensitivity, the transient climate response, and also the thermosteric sea level rise using the two-layer model. In fact, that's what's done in the AR6 sea level assessment. We don't use directly the global mean CMIP6 sea levels. We use a two-layer model emulation of it so as to get better statistical sensitivity as we run under different forcing parameters and under different regimes. So let me say that again. We can build this model for any of the CMIP6 models. Using that, we can predict key climate change indicators like thermosteric sea level rise, equilibrium climate sensitivity. And now we're going to go and look if the initial mixed layer depth tells us anything about how those model parameters vary. And this is basically the slide that shows that it does. So I'm going to jump through these panels of the right-hand figure slowly and try and give you an intuitive feel for how to read them. But you can see before that we're going to look for a Northern Ocean impact, a tropical ocean impact, and a Southern Ocean impact of the mixed layer depth. And it's the initial mixed layer depth. So in present day mixed layer depth, if you like, from a climate change evaluation. And then you can see that they get these scatter plots on the right. So these are basically examining whether there's a correlation between that mixed layer depth and one or other of these model parameters on the vertical axis. And at the bottom, you can see the list of all the models, and we have the GIST models in there, and the GFDL model is in there. So I saw some people from those places, so off we go. Okay. This is the Northern Ocean initial mixed layer depth. It correlates very strongly with the production of North Atlantic deep water. So look at this left panel, the little white bar at the top indicates where we're taking the average mixed layer depth, which is roughly the region of deep convection in the North Atlantic, plus a little bit in the North Pacific, but mainly North Atlantic is what's determining the variability. This is showing the change in potential temperature at depth across the multi-model ensemble with the mixed layer depth in that region. So when the mixed layer gets deeper in a given model versus the ensemble mean, what happens is you get hotter North Atlantic deep water and colder bottom water down below on the northern side of the Earth. And you might say, well, that sounds an awful lot like an exchange parameter between that surface layer and the deep layer. And so when you look for the exchange coefficient between the surface layer and the deep layer, yes, it does have a pretty strong correlation across all of the different models with the Northern Ocean initial mixed layer depth. So the deeper the mixed layer is in this Northern Ocean region, the stronger the connectivity is between the two-layer model surface ocean layer and deep ocean layer, as diagnosed and tuned in each of these models. The p-value is tiny, so this is highly statistically significant. The R value is telling you that there's a lot of other variability due to other things, this is just looking for a univariate relationship between northern ocean mixed layer depth and that exchange parameter. We can move on to the tropical ocean. The tropical ocean has a very different pattern of correlated potential temperature with the tropical ocean mixed layer depth region. This looks a lot more like you warm up more where the mixing gets stronger. So when you are mixing down in the tropics, we know that's actually in the subtropical cell region and a lot of that. So there's upwelling. So essentially your upwelling and your exchange with the surface is coming in between the two. You get warmer, kind of 1 kilometer-ish depth water masses in that kind of intermediate waters. And you also get some effect in the north. You don't see a big cooling effect here, except very deep, and that's not a very large cooling correlation. This looks an awful lot like what you think the Hasselman model would look like. When you change that depth, you get deeper warming, and that deeper warming hooks up to what's going on at the surface. Interestingly, the strongest correlation with the tropical ocean is actually the efficacy parameter. So the efficacy parameter, remember, is the one that determines whether you resolve an anomaly in the surface layer by linking it to the deep layer, or whether you resolve the anomaly in the surface layer by dumping the excess energy back to the atmosphere and air-sea processes. So only one model is down here on the surface linked to the deep with those anomaly, and that's the NESM3. Most of the other models have an efficacy that involves a significant fraction of exchange with the atmosphere. That's where we link up to the story that Piers Foster and the Magic Group have been talking about the way that Torsten Maritzen have been talking about how cloud effects have a big aspect of, explain a large aspect of the climate sensitivity of Earth system models. We are not suggesting here that cloud feedbacks are not involved in this. In fact, the efficacy parameter has an awful lot to do with how sensitive the cloud feedbacks are to upper ocean temperatures. What we're showing here is just that the tropical ocean mixed layer depth is an indicator of efficacy. And so you put those two together, and again, you get a relatively low R-squared relationship because there's a lot of scatter due to other things, but there is a statistically significant, quite small p-value between these two. So the tropical ocean looks an awful lot like a Hasselman system. There's a strong air-sea interaction component. There's a warming layer that's moving back that could be deeper or shallower across the CMIP6 ensemble. That's what we think about for the tropical ocean aspect. And then maybe the most interesting of all is the Southern Ocean mixed layer depth, which is basically the ACC and its mixed layer. It would surprise no one who thinks about the Southern Ocean overturning that has a lot to do with the Antarctic intermediate water and the surface waters that come out of the ACC region and interact with the gyres. What is maybe surprising, I don't know, is the fact that there's a strong North Atlantic deep water connection to the mixed layer depth in the Southern Ocean. You can think of that in the kind of long range total Atlantic MOC picture, where it's the kind of Robbie Togweiler perspective that it's really the winds and the mixing of the Southern Ocean and have a lot to do with the overturning circulation of the entire global system. Or you can think of it as being, water masses are changing all throughout the surface ocean, and that eventually gets back up and makes some impact on the Northern Ocean. Doesn't really matter too much. The important thing here is that there is colder NADW when you have deeper Southern Ocean mixed layers, and warmer NADW when you have deeper Northern Ocean mixed layers. Why is that important? Well, that's important because if we just look at the global average mixed layer depth, these two effects cancel. And so we do not get the climate sensitivity of global average mixed layer depth is a very poor indicator of climate sensitivity in this two-layer model, whereas these regional mixed layer depths are a much better indicator because they allow for this cancellation. So models that have deeper southern ocean but the same northern ocean tend to have colder NADW. Models that have deeper northern ocean don't affect, no effect in the southern ocean tends to have warmer NADW. And so in this case, it's really the equilibrium climate sensitivity, or the estimate S, the effective climate sensitivity, which is at the end of a 150-year simulation, the equivalent of equilibrium climate sensitivity, that's most strongly correlated with the southern ocean mixed layer depth. And so here again, lots of scatter, a relatively over R value, but a very low P value. So a statistically significant correlation. Okay, so that's the big picture. Those are the three regions we have. The mixed layer in those three regions is doing something quite different to the deep water masses and the way that they're warming under these kind of climate change scenarios.
Hi, Bella. Sorry
Yes.
to interrupt. We have a question from John. John's raised his hand. Would you like to unmute?
Please.
Hi, sorry about that. Yeah, just a brief clarification. Can you describe that cancellation one more time that you talked about in that last panel?
Yes, it's easiest to see actually when we have the two side by side. So this white bar up here in the northern region is indicating where we're averaging mixed layer depth to give us our northern ocean mixed layer depth average. And this white bar in the southern ocean is where the region where we're averaging to give us our southern ocean initial mixed layer depth average. When we correlate what happens to the water masses in the latitude depth space with deeper southern ocean and deeper northern ocean mixed layer depths, this intermediate phase around 2 kilometers, like right in the center of the North Atlantic deep water, is of opposite sign. So a deeper northern ocean mixed layer depth tends to correlate with warmer NADW. A deeper southern ocean mixed layer depth tends to correlate with colder NADW. Does that make sense?
Got it. Okay.
So if both deepen together, say you crank up mixing in your model, you make both deeper, it's unclear who wins. If you crank down mixing in your model and you make both shallower together, it's still unclear who wins. But if you do something that's selective, like wave-driven mixing, which is stronger in the Southern Ocean than the Northern Ocean, you might cool your NADW. If you do something selective, like pay attention to deep convection and marginal seas, which will have a stronger effect on the Northern Ocean mixed layer depth, then you would warm the NADW.
Fantastic. Thanks.
Yeah.
Also, I think Stephen has his hand up.
Great.
Yeah, Baylor, thanks for the. Can you go back to the previous slide? I just wanted to have your comments on the motivation for the latitude bands. I mean, in particular, you're missing the Gulf Stream, the Mid-Atlantic region and the Mid-Pacific region.
Absolutely.
The blue regions. And did you do that correlation with those regions and find less interest?
We were following a little bit of the literature about some other folks had looked for regions for one or the other parts of this story. But really, we were hunting for ones that had strong correlation. So we were looking for the mixed layer depths that covaried. So we looked at, a Hobmuller diagram of mixed layer depth as a function of latitude, as a function of time across the different models, and looked for where the big signal variability was. And it seemed to be isolated. These three regions tend to pick out the clearest signals. You certainly could do more. There would be no reason why you couldn't add more mixed layer depth boxes into this. We just realized that we couldn't do it with one global ocean mixed layer depth box, even though that was our expectation based on the Hasselman model. So that was the key piece. I'm sure you could, you can always make it more complicated, but we thought this was a minimal level of complication.
Okay, thanks.
And so we can now make a big matrix of all of the cross correlation. So this is everybody to everybody. And so these top 6 rows are the 6 parameters of the 2-layer model. Then we look at effective climate sensitivity, the transient climate response in the next two rows. Then we have the global ocean mixed layer depth, and then the northern tropical and southern ocean mixed layer depth. And then we're seeing what they're correlated with. And so that response that I just gave to Steve is kind of apparent. So if you look at the global ocean mixed layer depth column, which is this one, there are some statistical significant changes within the different model parameters, like the heat capacity of the surface ocean, which makes a whole lot of sense. But the climate sensitivity is not very strongly correlated and not statistically significantly correlated with the global ocean mixed layer depth. Whereas if you look at the North Ocean mixed layer depth, many of the model parameters are highly statistically significantly correlated, including the one that I showed last time, gamma. That's the one we just saw in the image. Plus, the effective climate sensitivity is now statistically significantly correlated. The tropical ocean, the efficacy is highly correlated. That's really important, but not the climate sensitivities. And then the Southern Ocean, the climate sensitivity is highly correlated, but of opposite sign to the Northern Ocean mixed layer depth. So these boxes are really kind of the minimal ones that we thought that pulls out why there is not a good prediction of climate sensitivity from global ocean mixed layer depth, and the cancellatory nature of the northern and southern, and the key aspect of the efficacy really being governed by some kind of tropical coupling between the upper ocean and the atmosphere. So I hope that sounds familiar to people based on their kind of dynamical preconceptions of how these systems work. That's where we came down to. We also dug a little bit into how the AMOC strength and depth works, so that we could see whether those were important or not. We have an initial AMOC depth and then a final AMOC depth, and it's quite a bit more difficult. Lorzana and others have been looking at AMOC driving these kind of climate sensitivity questions. So this is a more complicated story because the AMOC depths change quite a bit during the simulation, and the AMOC strengths change quite a bit during the simulations. And the initial magnitudes of AMOC and depths of AMOC do not predict well the final magnitudes and depths of AMOC across the model ensemble. So knowing today's CMIP6 model simulation AMOC depth is not a good predictor of future values. So this is an interesting diagnostic, but it's not, we don't think it's as directly useful as these mixed layer depths for that reason. Okay. So now we go into the fun stuff, which is we use the mixed layer depth as an emergent constraint. So we now correct our mixed layer depths in those three regions to the observed values and push through all of the correlations in the two-layer model coefficients that result from that. When we do that, we get a narrower ensemble spread of two-layer models than the original CMIP6 ensemble spread. So you can see here, this matters quite a bit in both the abrupt 4 times CO2 simulations and the 1% CO2 simulations. It has a pretty persistent signal all the way out to year 4000 as you go. And remember, this is based only on the initial mixed layer depth. This is not a time, we don't need to have any future information to narrow this ensemble window. An interesting way of thinking of this is how much remaining warming is there from the warming level you've seen at the present date. And so the remaining warming, starts off high and then drops down as you move forward in time. That's just what this panel B shows, is the remaining warming across this the total ensemble. But then you can ask what predicts the amount of remaining warming. And you might say, well, today's temperature should be a pretty good predictor of today's temperature difference from pre-industrial should be a good predictor of the remaining warming. It is, but it's not as good of a predictor as knowing the before the forcing mixed layer depth is. So this correlation here on the vertical axis in panels C and D is predicting the amount of remaining warming in any given year based on the initial mixed layer depths. So there is a lot of predictive power in knowing the distribution of initial mixed layer depths across your model ensemble. It's actually quite complicated to decide how it is you want to take those cross-correlated matrix of all of those different coefficients and then constrain the mixed layer depth. So rather than choosing one method as our favorite, we did 4 different methods, which are based on kind of simple linear algebra or more sophisticated bootstrapping or Monte Carlo methods. Those are what these 4 gray bars show. So there's fair consistency. They differ a little bit in how they handle the cross correlations across the ensemble. But the important thing here is when you compare these to the kind of box and whisker, which is just the statistics of the original CMIP6 ensemble, which is also showed here in symbols, you can see that the median value doesn't jump much in these 4 approaches from what it was before. This is just for the 6 2-layer model parameters, but the ensemble spread drops considerably. So basically we're removing noise across the model ensemble or uncertainty across the model ensemble by constraining the model mixed layer depths to the observed mixed layer depths. And the observations we're using are the Argo-based climatology of the Lynn Talley's group put out its scripts. And this is a bit flip, but anyway, apparently this is worth trillions of dollars if we can do it right and people act on it. So I don't know this person, this economist who made this estimate, but I'm very happy to say that our proposals based on this will be saving trillions of dollars. I also want to make one other quick acknowledgement, which is this study would not have been possible were it not for the Pangeo repository put together by Ryan Abernethy and others of the CMIP6 ensemble data. We did not have the resources to download all of the variables that we wanted from the original IPCC resource. Galen was able to write almost all of these diagnostics just by calling the Pangeo cloud repository, which is an amazing thing to be able to do. Okay, so we don't have a whole lot of time left. I just wanted to give a quick reason why we think the mixed layer is interesting, which is we know a lot about the dynamics of the mixed layer. We know a lot about the processes that are involved in changing the mixed layer depth. My student Ching Li just recently completed his PhD doing this. Another of my students, Abigail Bodner, who's going to be speaking later in this series, spent a substantial fraction of her PhD thesis thinking about the processes that affects mixed layer depth. So let me give you a quick tour of those results. Langmuir turbulence is one way that we can change the mixed layer depth. This is frequently excluded in the consideration of parameterizations of upper-ocean mixing. Langmuir turbulence is a beautiful process and phenomenon on its own. It's a wind-driven form of turbulence. So if the wind and waves coexist at the surface rather than wind only, the boundary layer turbulence is able to energize itself more. And so you get more entrainment, you get faster mixing, you get different air-sea fluxes because of it. This is just showing large eddy simulations on the right and some complicated things about analyzing large eddy simulations on the left that I'm not going to explain. And so you can parameterize Langmuir turbulence. And this is a table showing RMS errors, basically saying that if we do a good job at parameterizing Langmuir turbulence, we can reduce the RMS error in mixed layer depth in almost these same regions, the global, Southern Ocean, Northern, and tropical ocean in this case, but there's also a Northern Ocean analysis that you could think about analyzing in this way. So like I said, the wave-driven mixing is really important in the Southern Ocean. That's why I knew that, is because we've been doing these studies. You can also do it wrong. You can make your model much worse by putting in Langmuir entrainment or something else without paying careful attention to LES results and really understanding the process. I'm going to skip over that part, but just say another aspect that Ching has worked on is analyzing all of the present parameterizations, one versus another, and how they differ when forced realistically. It's a quite difficult problem. There is a big scatter among all of the parameterizations, even not including Langmuir turbulence, and then including Langmuir turbulence, of course, makes them more complicated. So we have a long way to go before we think we're done with Langmuir turbulence parameterizations. And then Abby's contribution to this was to follow up on the work that Ralph Ferrari and Bob Hallberg and I did on parameterizing submesoscale mixing in the upper ocean. And so this basically says the mixed layer is not totally mixed. There are lateral density gradients, fronts, and these fronts are critically related to frontal instabilities, mixed layer instabilities that restratify the upper ocean. When they restratify, it's harder to mix, so the mixed layer gets shallower. This is a little movie is showing what those instabilities look like, and these are observations of those mixed layer instabilities that I've shown many times. You've probably already seen before. But these are complicated phenomena as well. They're very small, only single-digit kilometers in scale, and other submesoscale instabilities, frontal instabilities, are even smaller. So hundreds of meters, tens of meters in scale. So we have to parameterize these kind of phenomena if we want to understand their impact on mixed layer depth. And again, lots of geographical specificity. We need to use large eddy simulations like this one to simulate all of the complex processes in the mixed layer to try and put them together in the right balance to get the mixed layer depth balance correct. And Abby's contribution was to take this rather complicated formula, which does a decent job of parameterizing that eddy-driven overturning and restratification of the mixed layer. This is just a comparison between an idealized simulation and the parameterization. And to make a new frontal width scaling that depends on surface forcing. And this is a beautiful piece of work, which I hope she talks to you when she comes to speak to you later, but I think it really enhances the robustness and the physical underpinnings of this mixed layer eddy parameterization and how it's implemented in climate models. And with that, I will skip over the results and just say, when you boil this all down, we see that equilibrium climate sensitivity for the particular CMIP6 model collection goes from 4.51 C with a likely range of 3.1 to 5.7 to 4.66. So only a tiny increase in the overall sensitivity, but a pretty substantial 40% reduction in the span of the uncertainty range. Even though I wasn't able to calculate this in time for this talk, we think that the thermosteric sea level rise equivalent from the two-layer model will also see an approximate 40% or so reduction in the span of the uncertainty range because of the close relationship between energy and the ocean heat uptake and the thermosteric sea level rise. And that's where I will conclude. Thank you very much.
Thank you very much, Baylor. That was fascinating. I should have some can clapter or something, can clapping or something. But then, do we have any questions from anyone? Oops.
I make this smaller so I can jump back and forth.
We've got a few people virtually clapping. John, okay, yeah, a couple of people put their hands up. I think John was first, and then I'll ask Mark.
Thanks, Baylor. This was a really, really fascinating talk. I really, really appreciate it. I don't doubt at all the mechanisms that you've highlighted, particularly in Galen's work, where you relate the mixed layer depths of the different latitudes to the interior temperature changes. Mm-hmm. When you look at the emergent constraints, though, the R² values generally are really small. And you point out that the statistical significance of those relationships is pretty high, and the R² is low values are likely due to other processes at play. I was wondering if you could comment a little bit more on what those other processes in general are and how you reconcile that with the fact that you still get such large reductions in your uncertainty when you apply the emergent constraints going forward in time. Does that mean that on long time scales, that other variability just doesn't matter, or how should you interpret that?
Well, one way in which to understand the lowered R² values is that the three different regional mixed layer depths are actually in competition to set some of those parameters. They're all correlated with all of the parameters somewhat. So an R squared is looking for a univariate relationship between one of the three regional mixed layer depths and that particular parameter. So the Northern Ocean, Southern Ocean cancellatory effect on the North Atlantic deep water means that they have a cancellatory effect on the upper ocean, deep ocean exchange coefficient. And so that's part of the reduction. It's just that an R squared value is a univariate measure rather than a multivariate measure. So when we do the emergent constraint, when we enforce the emergent constraint, we are actually using a multivariate approach. So that sort of boosts the signal that we can reduce a bit. But there are lots of other things that are going on, like Steve Griffey's question about what about the other places than the mixed layer depth that you're not looking at? Sure, that's conceivably another mechanism. But there are all kinds of other things like eddy parameterizations are different across these models. Numerics are different. Resolution is different. All of those aspects are just on the ocean side. We would expect to have an impact on the diagnosed coefficients. The key difference is mixed layer depth is observable. So it's an emergent constraint, unlike a unobservable model parameter, or an interpretable maybe, but unobservable model parameter. Plus, there's all of the coupling with the atmosphere, cloud parameterizations, coupled mode variability. We know all these CMIP models have really different interannual mode variability, and all of that. That's playing into this and widening the spread, adding to the noise among those. So the next step is now to go away from a correlative approach and to try to cause a mixed layer depth change in these regions and better track what goes next. Like, we're just looking at correlations now. What if we change the mixing in a particular region deliberately? Do we get the same class of response? Do we get a sharper signal? Does the R squared response go up in that case, where we have better control over all these other feedbacks into other aspects of the system? Does that make sense?
Yeah, that's a lot better. Thanks.
Yeah.
Thanks, John. Next we have Mark.
Baylor, hello.
Hi, Mark.
Long time.
Yeah.
I have a cold at the moment. You can hear that. But when you define mixed layer depth, what do you do about seasonality?
So we're using a mixed layer depth, which is an average, like a seasonal, it's a short-term average at the beginning of the run. So we're only looking at annual variations in mixed layer depth when we're doing the diagnosis. When we're talking about the observations we're comparing to, we are treating those in a similar way. But since the observationalists like to use other things other than mixed layer depth thresholds, we were as generous as we could be, and we took all of the different definitions that were readily available from Len Talley's group and put a box around them. So to say, we want the highest possible high estimate of mixed layer depth as observed and the lowest possible low of mixed layer depth in annual average observed in those regions. And so then when that's what we're comparing back to our short time scale average from the CMIP models. The mixed layer depth doesn't trend that fast in the CMIP 6 ensemble. So there's a little bit of annual variability to worry about, but the trends are not so great that you have to worry about the mixed layer depth changing fast or how you handle that.
Well, one of the things I wondered about is the one idea that you form a deep winter mixed layer, shallows in the summer, and that's one way of exchanging water out of the mixed layer into the deeper ocean. So that would say this winter-summer difference might matter.
Absolutely. I mean, we argued that Stommel's demon, that mechanism, that it's really the deepest wintertime mixed layer that gets subducted, is surely at play here. We could add more mixed layer boxes. We certainly could add a wintertime mixed layer and a summertime mixed layer. And I suspect we would get more explanatory power that way. I don't know whether it would pass tests for model parsimony, but I suspect it would. I agree that that's part of the process that almost surely would make sense here.
Anyway, it's very nice work. Thanks.
Yeah, thank you, Mark.
Thanks, Mark. Thanks for braving with the colds and everything. Do we have any other questions? Silence. It's a little quiet.
Silence.
Sometimes someone will be struggling to unmute, so just give it a minute. Someone might emerge.
Well, if not, thank you all very much for spending the time, and I'm happy to answer any questions that come up. If you want to read the paper, we have a PDF of the submitted version available on my webpage. So you can Google me and find this, take a look. Feel free to offer suggestions. We're still at a relatively early phase of this process. So I think, there have already been some good suggestions and things to think about now.
Thanks very much, Baylor. Just give it another moment, see if someone pops out. Okie doke. We're just coming up to noon now, so probably I should let people go. But thank you again ever so much. We look forward to. I think we have your student or someone, your previous collaborator, on later in the series.
Yes, Abigail will be speaking to you soon, so you should look forward to that. She's an excellent speaker.
Very much looking forward to that.
Nice to see you all.
Thank you, everyone, for joining us. Okie doke. Thanks, Baylor. Look forward to uploading this.
Yes.
Oh, I should have asked you. We like to record these talks.
Would you like me to upload? Yes, I'm happy to upload. Where would you like it?
Oh no, I'm happy to upload it. So I've recorded these to the cloud. Are you happy for me to upload it to the YouTube?
Oh yes, sure.
Yeah.
Sure. Yeah. If you provide me with the link afterward, I will. I'll repost it too.
I'm happy to send it to you before I put it up if you want to check if there's any errors or anything like that. But it was flawless.
I don't think I screwed up and swore in the middle or anything. Or the thing that I have actually had to correct, and occasionally I've had I used to have a laptop camera that I would record myself while teaching on that was sort of at belly height. And one day I was wearing a very short shirt, and every time I raised my hands, my belly was exposed right in front of the camera. So I had to go and clip all of those moments out before posting. I don't think I did anything like that today. So
I think it's sometimes nice to have those moments. It kind of makes someone more
relatable or something.
Yeah, relatable and warm and what have you. Yeah.
Yeah. So
it's a fun tone to it. Anyway, thanks ever so much again. I'll let you go. Yep. Sure. Hopefully we'll see you again.
So did you say you wanted the PDF or you don't need that?
Gavin looks like he's just put up the PDF for your paper on these models.
Yes, he posted that, which is great.
Yeah.
Yeah, but if the PDF of the slides, if you'd like it, I'm happy to give it to you too. Whatever.
That'd be great. I can add a reference to that. We don't currently have like a repository for the slides, but actually that might be a really nice thing to do because we could put a link to the slide in the description of the YouTube talk. I can definitely put this link to the paper in the description of the YouTube
Absolutely.
talk. That's
great.
really neat.
Okay, thanks very much, Craig. Nice to see you. Thanks for the invite. This is a really interesting series. Presently my group meeting is at exactly this time, but I may hope to catch some of the ones in January. So
okay,
thanks for setting it up.
Thank you.
Yep. Bye-bye.
Cheers. Bye.